Swayam Prabha. Digital India. Educated India.
Welcome. So, we are discussing finite element method for Timoshenko beam. In the last lecture, we discussed how to derive the governing equation from the energy expression of a shear deformable beam, basically thick beam, not thin beam, that we have learned in earlier lectures, that is Euler-Bernoulli beam is the thin beam where the shear deformation or shear strain is essentially 0. But here the shear strain is actually constant, and we also introduced to consider the quadratic or the parabolic variation of the shear strain, which is coming from the equilibrium equation that actually is modified using the shear correction factor. So now also in the last class we have discussed the classical Rayleigh-Ridge method, where I have shown you one small example, just how to discretize. For instance, if you remember, the theta and w both are variable here, so independent variable, that is the not the dw dx, theta is not dw dx for Timoshenko beam. Now, now from this lecture onwards we will discuss the finite element method and its discretization for Timoshenko beam. Now, so we will start with the weak form, then we will just see if this theory has to be valid for the thin beam, that is when theta is actually dw dx, then there is a problem. So, that actually generates the shear locking term or the shear locking in finite element method. Though shear locking will be discussed in detail in later lectures, but I will give you an impression how shear locking comes into that. Comes into picture, and then we will discuss the consistent interpolation and stiffness matrices. So, to start with, we will just a small recap. So, if you remember that we have primarily seen the governing equation as of the Timoshenko beam is this ddx of Ks is the shear correction factor, Ga is shear modulus, A is the area, and then that is equals to dw dx minus theta x or theta into plus q. So, if I just take the vertical that means the vertical direction, then it can be written as minus q also. So, if I consider this kind of beam where the q of x is constant or q0, or it can be function of x also. So, something like if you want to derive a triangular load or something like this. So, this is a function of qx. So, basically this can be q of x equals to 0. Now, another equation that evolved, because theta is also an independent variable. So, this equation is like this, that ddx of ei d theta dx. So, ei d theta dx is the moment here, and then shear correction factor, that is ksga into your dw dx and minus theta. So, that is equals to 0. So, here the main assumption is that theta is not equals to dw dx. So, if you put theta equals to dw dx, then this becomes 0. So this equation becomes 0. So now your strain energy will change actually. So now from there you will get the, if I try to minimize it, you will get the standard Euler-Bernoulli equation or governing differential equation of the Euler-Bernoulli beam. Now also, if you remember that we were following some sign convention, that is theta is d minus dw dx. So that means the negative of this. So you can use the plus, but for just consistency, the negative of derivative of dw dx we were considering. So this was the Euler-Bernoulli beam assumption. So if I just, instead of dw dx, if I just put negative of this, if I consider, that means considering the sign convention, that is if the beam deflects like this, that means this one is actually my positive and corresponding opposite. So I can just write this equation is like this, that dx of k is ga into dw dx plus theta. So that means I have just taken minus common. So in place of dw dx, I am just substituting minus dw dx because of the convention that we followed in the Euler-Bernoulli case. So that's the basic thing. So now if I just take this thing into consideration, that is ddx of ei d theta dx, then if I consider this, that is minus ks ga into dw dx plus theta equals to 0. So now naturally these two equations we have. So we'll first start with the weak form, that is how to draw or how to form its weak form. So since theta and w both are independent variable here, or that means the primary variable essentially. So these two primary variable will obviously will have two different weight functions, and remember that theta and w are of not same unit. So that's why one of them is displacement and one of them is rotation. So let us consider V1 and V2, both are weight functions. Corresponding to that, we will consider the weak form. So now if I just multiply this, that is minus of V1 into Ks Ga into dw dx plus theta minus will be plus qx into dx, that is equals to 0. So this is the first weak form, and the second weak form is again in terms of V2. So V2 ddx of ei d theta dx minus ks ga dw dx plus theta. So this is my second weak form, that is equals to 0. So now again integration by parts. So the next step what we will do is that we will just integrate in by parts. But if you look carefully here, that okay, I missed one ddx here. So that is ddx of this. So if you see this, now you will see that this is actually a second order equation. So the if I do the weak form, then what will happen is that integral, so this is from 0 to L. I'm just taking that area and moment of inertia I. So I can write 0 to L, and then this is nothing but dv1 by dx into Ks Ga, and then d w dx plus theta. That is my this thing, and then we'll have this forcing term and then boundary condition, that is qx into v1 dx. Then we'll have the boundary term, that is your ks ga dw dx plus theta into v1. So this term has to be at x equals to 0 or x equals to L. So this is equals to 0. Now you see this term is essentially is a weight function, and this term is the shear force essentially. Now the second weak form, if I write similarly, then again what I will have is dv2 dx and then ei d theta dx. So this is into dx, and then the second term here, I don't need to do the integration by parts because this is a first order term. So only derivative here is dw dx. So naturally so this will be let us consider minus, then if I take minus common, then this will be plus. So integral 0 to L v1 or v2 ks ga into dw dx plus theta. So this is into dx. So this is the stiffness term. So first one is the pure bending term if you compare with the Euler-Bernoulli theory. Now here there will be a boundary term will come from here. So this boundary term will be your minus v2 into ei d theta dx. So naturally if you see this, then x equals to 0 and x equals to L. So now if you see this, so this is your boundary term. So this term is essentially the moment, and this term is rotation, because v2 is corresponding to the variation or the weight function corresponding to theta, and v1 is or the weight function corresponding to w. So naturally this v2 has to be the rotation. So either shear force and displacement has to specify, or the moment or the rotation has to be specified. So these two equation, if I make it to 0, so this is my standard weak form for the Timoshenko beam element. Now the primary case here is if you compare with the standard beam theory or the Euler-Bernoulli beam theory, you will see that the weak form contains only first order derivative. So first order derivative means, that means your continuity requirement is actually less. So and also you don't need that slope continuity. So that means that theta need not be dw dx, because theta is an independent or primary variable here. So dw continuity of dw dx is not required. So naturally the standard choice is the Lagrange type of element. But before that, let us I will come to that later, but before that, let me bring it to the discrete form. So now let us say W we discretize like any standard Lagrange element, for instance quadratic, cubic or linear. Let us write this is that summation of uh, phi I wi, and theta also we write, that is summation of so phi j or let me use different variable, so that is psi I theta I. So basically what we are looking for is that a beam element that is two noded, whether it will be two noded or three noded, I will come to that later, but let us say this is slope interpolation and displacement interpolation. Now here if I now substitute phi I for the V1, that is my V1 is the weight function and V2 corresponds to the rotational weight function. So, psi I, if I substitute here, then my weak form will look like this. So, integral 0 to L d phi I dx into Ks Ga into d phi j dx. So this is the part actually Kij. So now actually this is summation. So into dx, and then the theta term will have again integral 0 to L d phi I dx into Ks Ga into your psi j dx, and then you will have your moment equation, that is not the force equation, that is qx into psi phi I dx and the boundary terms. So that is let us say the boundary terms will be q1 and q2. So likewise we can discretize. So phi j and sorry phi I here. So phi I into your this Ks Ga and your dw. So we don't write like this. So let us say this is your shear force. So let me now define the shear force. So this is we can write it also in terms of Q1 and Q2. So V1 or the phi 1 phi I, that is Q I. So that is x equals to 0 and x equals to L, that is equals to 0. So now this is for the first one, and the similarly if I substitute the second one, then it will look like 0 to L, that is your d psi I dx ei d psi j dx. So this is ijth entry, okay. So remember this is ijth entry. So now there is a summation here. So there will be a displacement vector corresponding wj. So this is wj and there is a theta j, right. So these things you I'm just escaping. So this is just to describe you. So I will write the discrete form in just now. So this is dx, and then you will have theta j, right, and we will have this is 0 to L, then this we again you will have a term which is corresponds to the this term and theta. So naturally you will have psi j or psi I and then k s g a into first let us say theta. So theta j into theta j dx, then another term will be there, that is integral 0 to a corresponding to dw dx, that is psi I k s g a into your d phi I phi j dx into wj. So that minus your psi I into your qi, that is x equals to 0 to x equals to L. Now this if I write it in the suppose I discretize with two noded element, that is a linear Lagrange polynomial. So for instance let us see what happens if I discretize with two noded element, that is w1 w2 theta 1 theta 2. So two variable and L is the length. Then what will happen is phi 1 phi 2 are w interpolation. So phi x is phi 1 w1 plus phi 2 w2, and then psi theta x is also I am taking phi psi 1 w1 plus psi 2 w2. Now phi 1 and psi 1 we know from our previous knowledge, this is just this. So this is a linear Lagrange polynomial. Similarly this is equals to psi 1 psi 2. So same interpolation for the displacement and rotation. So now if I do that and if I write its matrix form, this equation if I write it in matrix form, so I will get the stiffness matrix. So now stiffness matrix will have two components. One is your let us write it K11, right, and then K12 will happen, and then K21 will happen, and K22 will happen. So this multiplied by your W vector and theta vector. So W vector is essentially vector W is your W1 W2. So this is different than what we did earlier for the beam. Now theta vector is actually theta 1 and theta 2. Now this will and these terms will, this term and this term will contribute to my force vector. So essentially we'll have a force vector. So f of 1, f of 2, and we'll have q of 1 and q of 2. So now first let me write down the expression for this k11. So k11 ij will be first term which is corresponds to w. So this term will be k11 ij. So this is equals to integral 0 to L d phi I dx ks ga into d phi j dx into dx. So this is my first stiffness matrix term. So this actually is this. So now if you have a two-noded interpolation for W, then this term will be actually ij will run from 1 to 2. So kij K11 matrix. So remember these are the sub matrices. So these sub matrices will be 2 cross 2 if I use a linear Lagrange polynomial. Now similarly K12 ij will be something like this, 0 to L, your this term will be your Kij. So K1 to ij. So that is d phi I dx ksga into psi j. So here you see this term will also be 2 cross 2 matrix. So this term will also be 2 cross 2 matrix. Remember, we have assumed that it is a 2 noded and linear interpolation. So similarly, if you have K21 is actually Ij if I write, then K21 Ij will be this term actually. So in terms of Wj, because Wj is here. So that's why this is also a 2 cross 2. So if I write it 0 to L, that is psi I ks ga into d phi j dx and into dx. So if you see, compare this K21 and K12, you will see this is K1 to Ij. Okay, so sorry, K1 to Ji. So K1 to Ji. So I can, from these expressions, I can say that this K12 transpose is actually K21. So this is just transpose of this matrix, which will that is a good thing, because it will maintain the symmetry of the stiffness matrix. Now what will happen to K22? So K22 Ij will have K22Ij will have your integral 0 to L. So this term will be there. So d phi psi I psi j dx d psi j dx into dx, plus this term will also be there, because this is also a theta j term. So this will also include my psi I ks ga into psi j dx. So this is my theta term, total theta term. So now you will see that this matrix is also a 2 cross 2, because this is linear interpolation. So this is the overall weak form. Now the forcing terms, as usual, you can do. So W, if I write the Timoshenko stiffness matrix Ke, so Ke is having this thing, and if I write generalized displacement like this, so if I write this form, so Timoshenko stiffness matrix will have two components, that is two submatrices, that is K11, K12, K12 transpose. So I can just write transpose, and then K22, and then this W bar will be something like this, that is W1, W2, the theta 1, theta 2. So this is linear thing. Now then F will have two components, that is your small f1, small f2, and then sorry, this will have this thing. So small f11, f12, small f11, sorry, f21, f22. So this will have this thing, plus you will have the shear force Q1, Q2 or Q3, Q2, Q4. So these are the shear force. First two are shear force, and second twos are moments, that we can easily see from the boundary condition that we derived earlier. So this is nothing but the shear force, this term, and this is nothing but the moment, because if you see the boundary term, so this is just moment. So this is just moment, and this is shear force. So this is shear force. So first two term of Q matrix will be shear force, and second two term of the this thing are moment. Now what will happen if I just put this thing, use the this linear interpolation, what will happen? So let us see. Our W is interpolated like this, that is 1 minus x by L W1 plus x by L W2. Now theta is also interpolated, 1 minus x by L theta 1 plus x by L theta 2. Now both two, if now I consider a thin beam, so suppose this is for thick beam problem, so we don't know that it is a thin or thick. So this theory, if I try to apply in the thin beam, where essentially your theta will become dw dx or minus dw dx, whatever you call. So then what will happen? Then from here, if I consider dw dx, then my dw dx is simple, that is d2 w1 minus w2 by L. So this is a constant slope. So that's what we observed in one beam problem that I did earlier. That's what we observed. Now in case of this is slope is constant. Now your theta x is actually a variable. So now theta x, if I this same theory, if I apply to thin beam, where theta will be linearly varying, but from displacement I will get a constant theta in case of a thin beam. So remember, I am just talking about thin beam now. So now if I just write this thing, so that means my theta x has to be consistent with dw dx in case of a thin beam. So that is dw dx. Now if I write now my theta, that is 1 minus x by L theta 1 plus x by L theta 2 should be equals to my w2 minus w1 by L. Now this actually, if I just write it, then that is x by L into theta 2 minus theta 1. So now this is a constant term, right hand side is a constant term. So naturally this term has to be equal to this. So if this term has to equal to this, then this has to be this has to be 0. So this will be 0 only in case of non-trivial solution, that is x equals to 0. This only when theta 1 equals to theta 2. That means theta 1 must be equal to theta 2. So now theta, that means the variation of theta is not allowed. First of all, so theta 1 and theta 2, if it is equal, then what will happen to our weak form? Because our weak form contains this term, that is the bending energy, bending strain energy, which contains actually if you write the bending energy is actually 0 to L EI by 2 d theta by dx whole square dx. So this is my bending energy. Now this, if theta equals to theta 2, that is theta is constant or slope is constant, then my bending strain energy will be 0, right? So that is not allowed in. So this is actually this linear interpolation or same order of interpolation is actually will create some problem. Because that will be inconsistent. So numerically, if you try to solve this problem with this, then you will find the finite element solution will be giving you, giving you the garbage value. So this phenomena is known as the shear locking or the mesh locking shear locking phenomena. So, this phenomena is known as the shear locking phenomena. So, this phenomena will study separately in the later later part of the course, but you must remember here that if I just use the same order of polynomial for instance linear polynomial for the displacement as well as the rotation interpolation or the slope interpolation, then what will happen, that is inconsistent with the theory, because when the beam thickness becomes less, that will be thin beam. In case of a thin beam, we are approaching in thin beam regime, then the constant slope will produce your zero bending strain energy. So, only shear strain energy will be activated in the system. Bending strain energy won't be activated because it will be zero. So, that will started giving you the garbage value in finite element formulation. So, if you code it and if you see, then you will find it out that this will produce a garbage value. So, naturally to avoid this phenomena, this shear locking phenomena in solving Timoshenko theory based finite element, then we have to choose a different strategy or different methodology how we choose the polynomials. So, the one of the solution of such to circumvent this issue is to use a consistent interpolation. So, consistent interpolation is consistent interpolation. So, what is consistent interpolation? Consistent interpolation is this, that our main problem is because if I use the linear polynomial, then linear polynomial will produce a constant slope dw dx, and which is not consistent with the slope variation. So, if I choose my polynomial in such a way that dw dx and theta variation is consistent, then probably I can solve this problem. So, that means that the order of polynomial or the order of dw dx and theta should be equal. So, obviously polynomial order. So, polynomial order of dw dx and theta should be equal. So, that means if I use suppose quadratic polynomial for w interpolation, then naturally dw dx will be a linear polynomial. So, then and if I use theta interpolation as linear polynomial, then we will have the consistency, but that will also have some problem. We will discuss it. So, let us say that w is interpolating like this, that is phi 1 w1 plus phi 2 w2 plus phi 3 w3, and theta x is your psi 1 theta 1 plus psi 2 theta 2. So, now phi 1 we know what is the quadratic Lagrange polynomial. So, here we are not using any Hermite case because we do not need dw dx term to be continuous. That theory does not demand that. So, theta is phi 1 can be quadratic polynomial. So, quadratic polynomial we know the quadratic polynomial. So, that is 1 minus x by L into 1 minus 2x by L and then phi 2. So, if I have a mid node, then that is 4x by L into 1 minus x by L, and phi 3 is actually minus x by L and 1 minus 2x by L. So that is a quadratic polynomial, and the corresponding slope interpolation remains same, that is 1 minus x by L, and psi 2 is x by L. So that means this is linear one, and this is actually the phi 1s are quadratic polynomial. So now what will look like the element, my element will look like this, that there are 3 nodes in this element, but this node, the middle node, I have only interpolation about W. So this is allowed because two primary variable, that is W and theta are two primary variables. So this is naturally allowed. So W1 here I will have W1, W2 and W3, where I will have only theta 1 and theta, let us say this is third node, okay. So to make this thing, so this is only, or I can say like this, if you because if I do that, then this shape function might change. So W3, then let us say theta 3. So here only I will have a variable, that is theta 1 and theta 3, but at node 2 I won't have any variable. So that means I do have a node 1 and 3, but second node I don't have a theta interpolation, because I am choosing one order less polynomial for theta interpolation. So this is known as the consistent interpolation. So now if I do this, then naturally my d theta dx, sorry, dw dx will be same order of polynomial with theta, because dw dx will be a linear polynomial, and d theta and theta is actually a linear polynomial. So there is no inconsistency, and the bending strain energy will be non-zero, because linear will again d theta dx will give me a constant value of energy. So this will be non-zero. So we can avoid here, we can avoid shear locking here. So now if I try to do this, then what will happen? What will be the size of my stiffness matrix now? My stiffness matrix size will be now so how many degrees of freedom will have? W1, W2, W3, right? And theta 1, theta 2 will have. So, or theta 3, let us say, and so you will have 5 cross 5 stiffness matrix. So you will have instead of 4 cross 4 stiffness matrix, you will have 5 cross 5 stiffness matrix, because you have one more displacement nodes. So if I now start doing this in this process, then this stiffness matrix you can just substitute here this stiffness matrix. So this one is the first stiffness matrix is K11 submatrices, K11, K12 and so on. This can be very easily done by just substituting this phi 1 and psi 1. So let me just write, because we have already derived this thing earlier. So K11 ij, if you see, that is 0 to L d phi I phi j ks g a into d phi j dx. So this is a if you remember this, then this is a quadratic bar element. So but the stiffness is different. So ksga by 3l into, this is something like this, that 7 minus 8 1, then minus 8 16, then minus 8 1, then minus 8, and then again 7. So this stiffness matrix we have derived earlier. So if you just substitute phi I phi j, you will get K11. Now similarly K21 or K12, if I just do it, K12, so that is 0 to L d phi I dx into your ksga into psi j dx. So, this if I write it, then this looks like ksga. So, here it is a linear, remember, and this is also a linear, okay, because d phi I dx will be a linear polynomial. So, ksga by 6 actually. So, here if you see that this matrix will be a rectangular matrix, because ij variation, I will be varying from 1 to 3 and j will be varying from 1 to 2, because I is actually here I is actually the displacement interpolation. So, I have 3 nodes, so 3 shape functions, and j will be having rotational or slope interpolation or slope shape functions. This will have 2 nodes. So, j will be varying from 1 to 2. Naturally, this will be a rectangular matrix. So, this looks like -5, -1, 4, -4, and then this is 1 and 5. So, this actually will be 3 cross 2 matrices. Now, naturally, this will be as we have proved earlier, that is K 2 1 transpose. So, this will be K 2 1 transpose. Now, this similarly, if I just do K 2 then K 2 will have 2 terms. So, first one will be 0 to L d psi I dx into E I d psi j dx into dx. So, this will be your bending term, and then there will be another term, that is 0 to L psi I into ksga and psi j dx. So, this will give me K 2 which is actually a 2 by 2 matrix. So, this is naturally the linear bar element, if you have remembered. So, that is EI by instead of AE there will be EI. So, this is actually 1 minus 1 minus 1 1. And then another, this if you remember the mass matrix, then this is just psi I psi j. So, that is ksga L by 6, I think, then 2 1 1 2. So, this is my K 2 matrix. So, now with these submatrices I can write the stiffness matrix for Timoshenko beam element, that is K 1 K 2 1 and K 1 2 and then K 2 2. So, this is my Timoshenko stiffness matrix. So, this is one way to avoid the shear locking phenomena, by which is known as the consistent interpolation of the consistent finite element interpolation. So, by which we can compute the stiffness matrix for the Timoshenko beam. So, there are other ways which we will discuss in the next class. So, here I stop for this lecture. So, let us meet in the next lecture for the other method of avoiding shear locking. So, thank you.